Today will feel like a lot of review because it's supposed to be. This is something that you learned in Algebra 2, and it should have been early enough that it wasn't something that was cut out of last spring. And I know this is one of Mr. Michener's favorites, so you probably spent a lot of time talking about systems of inequalities in two variables, and that's good because, like I said, we're ready for something that feels just a little bit like review here before we get ready for our test. So we will be able to graph a linear inequality, graph systems of linear inequalities, solve a system of inequalities graphically, and then we'll get to the point where we solve a linear programming problem. I'm hoping that we get to one today that it doesn't have the word problems involved, and that tomorrow we can focus on the ones that have words that we have to translate into that system of inequalities. So the key here is remembering where do we find solutions to systems. And an ordered pair, AB, is a solution of an inequality in x and y if you substitute it back in as x equals a and y equals b, and it satisfies the inequality, which means it makes it true. You know, when you put your ordered pair in, you can say, yes, this inequality actually works when we do that. So a lot of times when you're graphing inequalities and you first start out, you do what's called testing a point. You know, you want to know where is the shading that you have to do. And so in this case it says, is the ordered pair 2, 5? Is that a solution to this inequality? Well, we need to plug it in and take a peek. So the 5 will go in for y. And then we'll do the math following the order of operations and see what we have over there. Well, 2 times 2 is 4, and 4 plus 3 is 7. So this says 5 is less than 7. Yeah, that's true. So is it a solution? Yes. The problem becomes with inequalities, there are usually an infinite amount of solutions. And so it's not something we typically want to just leave as, well, as this is with just one point. We'd prefer to have a graph that shows, hey, here's where all the solutions are. And that's what we do when we're graphing inequalities. So a graph of an inequality represents all the solutions of the inequality, and those are called a half plane. So back in geometry, you learned that a plane is if we could cover the entire world in a sheet of paper that has no thickness. That's what a plane is. And when we're talking about a half plane, we're trying to represent, here's a boundary line. All the answers are over here. That's what we're trying to show with our half plane. So remember, boundary lines are an important part of your graphical representation. Again, we know they should have arrows on them. This is just a screen capture by the book here where they get a little lazy and don't give us the arrows. And we know there's a difference between those boundary lines depending on whether or not we have an equals bar or not in our inequality. If we don't get an equals bar, we meet our boundary line, but we want people to know the numbers that are on there are not solutions. And that's what's happening here. This is dashed, and sometimes they'll be dotted. But what it says is, this is the cutoff, but these are not solutions right here. That's not going to work. And then we shade one way or another to show which of those two half planes we want here. So this one is just a graph of y equals 2x plus 3, which would be our boundary line if we made that into an inequality. So we have steps when we draw the graph of an inequality in two variables. And the first is draw the graph of the equation obtained by replacing the inequality sign by an equal sign. Pretend it's not an inequality for a second. Make it an equals, and then either put your line in slope-intercept form or use the zeros, use the x and the y intercepts to figure out where that will be graphed. But we do use a dashed line if we don't have the equals bar, and a solid line if we do. Solid is to show, yes, these numbers really work on this boundary line. And then check a point, test a point in each of the two regions of the plane determined by the graph of the equation. If the point satisfies the inequality, well, then that's the side you should be shading on. So shade the region that contains that point. Down here, we have graphing a linear inequality, and we want to draw the graph of y is greater than or equal to 2x plus 3 and state the boundary of the region. So again, they're saying pretend for just a second that it says y equals 2x plus 3 and figure out where to graph that. Well, this is in slope-intercept form. So we'd go to 3, the y-intercept of 0, 3, and then we'd use the slope to go up 2 and to the right 1, and as usual I'm going to do that several times and backwards to give myself something to aim at. But then we have to stop pretending. So now we have to think, well, did it have an equals bar? Because if it did, then I need to make it solid. And it did. It was y is greater than or equal to. So this will be solid. And then we test a point to see which way to shade. And if your line doesn't go through 0, 0, that is always the easiest point to test. So we're going to test 0, 0. And see if it makes sense in our inequality, if it's true. And this would say 0 is greater than or equal to 3, which hopefully we go, no, that's not true. So that means we don't shade on the side of the line where 0, 0 is, because that's not a solution. We shade the other way. Now, as your Algebra 2 book usually just says test a point and then do your shading. But I've always taught my Algebra 2 students, if it's on a test, test both sides, Make sure that you didn't mess up somehow when you did that. So it would also be a good idea to try something like -3, 0 in there and, make sure that it works if this is on a test. For homework, it's usually, pretty quickly done by just figuring out, does my 0, 0 work or not? So there we have it. Solid to tell people, yes, everything that's on this line is a solution. And the shading to show this is the half plane that we have to represent, because we had to show all the solutions. And there's an infinite amount. So we've got this little thing here that says the boundary of the region is, because it all comes from what we started with. That boundary line. And once we have that, then it's just a matter of testing points and seeing what we want to do. So, I'll review, right? Coming back to you pretty easy? Good. Good. So now, graphing linear inequalities, we're going to take a look at a couple of special cases here. Draw the graph of the inequality and state the boundary of the region. Well, since that's what we start with, I'm going to go right down here and say, well, if I pretended this was equals, it would say x equals 2. And some people get a little turnaround about horizontal and vertical lines. So just remember, if there is a giant XY Cartesian coordinate plane in front of you and it's over the entire world, you've got your X going this way and your Y going this way. To get its name, you have to karate chop that axis. So to get X equals 2, you have to karate chop the X axis, and your arm makes the motion of a vertical line. So this is a vertical line at 2. But I stopped myself because I want to think, well, dashed or solid? Which should it be for this one? Yeah, this is solid. It has an equals bar. And for this one, I don't think most of us would test a point. We'd look at that and say, well, I know where the x's are going to be greater than 2. They're going to be to the right of this. So we'd shade this way. And we've got it. Over here, we have y is less than -3, which gives us a boundary line of what? If you have to karate chop the y-axis, you have to go this way. That's going to be a horizontal line. Dashed or solid this time? Dashed. And we are at -3. And the question is, do you shade up or down? Which way? Yep. This one is y is less than. And we're shading down. So special cases here, horizontal and vertical lines that show up. Most of the time in our solving of linear systems, we're going to see that x is greater than or equal to 0 and y is greater than or equal to 0 show up a lot. And that's because in real life, most things can't be negative. So those are the ones that we have to graph a whole lot. But we still need to know that these are well, how to graph vertical and horizontal half planes as we go through this. All right, example 3, graphing a quadratic inequality. Draw the graph of y is greater than or equal to x squared minus 3. State the boundary of the region. So, hopefully, you've got a little picture of a parabola in your head. Y equals x squared minus 3. And the way we learn to graph this in Algebra 2 is through the use of translations. Come on, smartboard. Wow, that took a while. So we had you come up with a table for y equals x squared, which is our parent function for parabolas, and put the usual suspects in for your x values, and just square those. And before long, you had those memorized because you were graphing a lot of those at one time, seeing the translations. So this one, we have to move 3 units down because it has this minus 3 in back. That's its k value. So that we don't have our parent function graphed and what we have here for y equals x squared minus 3 graphed at the same time, because we already have a lot going on with these graphs. What you want to do is think, my 0, 0 is now going to be down here. So treat that like your origin. And when you graph, start from here and say, well, 1, 1 would be 1 to the right and 1 up. And 2, 4 would be 2 to the right and 1, 2, 3, 4 up. And then 3, 9 would be 3 to the right and 9 up. And like I said, that way you don't have the parent function and your y equals x squared minus 3 on there. And you can just use symmetry with the parabolas to get the other side. Dashed or solid for our little parabola? Does have an equals bar. And again, as long as my parabola is not going through 0, 0, it's a good idea. A nice little set of numbers there with 0, 0, especially when they're multiplying. And test it and see if it works. So 0 is greater than or equal to 0 squared minus 3. 0 is greater than or equal to negative 3. Well, 0 is greater than or equal to negative 3, so we need to shade inside our parabola. Because there's only 2 choices. You're either shading inside or you're shading outside. So if it works, that's where you shade. Now, we did learn, it was kind of a shortcut, and yeah, we don't technically like to use shortcuts a whole lot when graphing, but we did learn that when we have this in slope-intercept form, if this is greater than or equal to, you shade above the line. And if it's less than or equal to or less than, then you shade below the line. So that's a shortcut if it's y equals mx plus b when you graph the original. But testing a point is a very, very safe way to go, especially when we go from graphing lines, linear inequalities, to graphing parabolic inequalities. Because then you're using those same skills of, hey, I'm going to test a point and see if this works or not. So now, a solution of a system of inequalities in x and y is our objective for today. And the ordered pair xy has to satisfy each, or you could say all, of the inequalities in the system. Has to work for both. The good news for us is, by doing this graphing and shading, we are seeing where the solutions are. So we know that wherever the overlap is of our colors, well, that's where the solutions to both of them will be. So I have y is greater than x squared, and I think about that boundary of y equals x squared. And I realize, well, that was just the table we had on the last one there, but it doesn't have a k translation this time. So 0, 0, 1, 1, 2, 4, 3, 9, and the negatives by symmetry. Dashed or solid for that one? No equals bar this time. And again, you could throw in a 0, 0, but that's not going to help you much because 0, 0 is actually on this parabola. So maybe something like 0, 1. Well, that's going to say 1 is greater than 0, which it is, which is good news. That means we're going to shade inside our parabola. And now here's why I had you grab a second color. We have another one we're supposed to graph with this one. 2x plus 3y is less than 4. Now, with this one, our boundary would be 2x plus 3y equals 4. And when it's in that form, which is called standard form, usually the fastest and easiest way to get something graphed is to find its zeros, to find the x and y intercepts for the graph. Because 2 points determine a line. I mean, you've learned that in geometry. Point, line, plane, postulate. Any 2 points determine a line. But now what I want to do is make this a little bit easier and faster. So when I teach it in Algebra 2, I always teach the thumb method. You know, you think, hey, if my x is 0, well then anything multiplied times that x is going to be 0. So you cover up 2x with your thumb. And then it'll say 3x equals 4, and you can just solve that by dividing both sides by 3. So 4/3. And then over here, you've got your 0. Put your thumb over the y coordinate because anything times 0 is going to be 0, and this is gone. And you have 2 times something is 4, and that something is 2. Now, this makes me a little nervous because we're doing 0, 1 and 1/3, and 2, 0. And those are very close together on my graph. And especially on a test, if I start feeling like, I might not be able to get a really good idea of exactly where this line is going to go, I'm probably going to put it in slope-intercept form so I can figure out what the slope is and make sure that I'm graphing where I need to graph. So with our 2x plus 3y equals 4, we'd subtract 2x from both sides and then divide by 3. Well, double check. We're sure our 0, 4/3 is right, but now we also have the slope. From either one of those 2 points now, we could go down 2 and right 3. And that gives you a much better look at, where the line is going, what the slope is. So should that one be dashed or solid? That one's dashed as well. Doesn't have an equals bar. And it does not go through 0, 0 this time. So we could test 0, 0. And it would say 0 plus 0 is less than 4. Well, it absolutely is. So we need to shade on this side of our line. But the whole time that I'm doing that, I'm thinking, the solutions to the system, though, are only where I'm going to see both red and blue. And that's this little piece right here. Weird little kind of half-moonish shape that we see in there. So we overshade that because that's how we represent our solutions. Hey, this is where the solutions to the system are. Those are the points that work in both of those inequalities. So this one wasn't a linear system. We had a parabola and a line when we graphed this. And this one is asking us, how about those boundary points? Thank you. How about those boundary points? Are they solutions to the system this time? Are they or not? No go, right? Because both of these were going to be dashed lines. So we need to know that. We need to know, hey, which ones are actual solutions to the system. So we can't include what we see on the red or the blue line, so the red parabola shape. But what's inside there is going to be where we find our solutions. So now this one says, let's make use of our graphing calculator to just support your answer. I don't know that I would even do that with this one. But, you know, we're getting to the point now where this is starting to get more involved. We see there's 4 inequalities here. I would probably just use algebra for this one. When we get to the word problems later and the numbers are bigger, then yeah, you might want to grab a graphing calculator. But here's what I looked for first when it said solve the system. I looked to see, are we supposed to stay in the first quadrant? And we are. And how I know that is right here. X is greater than or equal to 0, and y is greater than or equal to 0. So I don't need to have any of the other quadrants for this graph. Then the next thing I want to do is figure out, well, do I have to do something like go by 5s, by 10s, by 15s, anything like that? And really, I'm going to color code like crazy on this one. So I'm going to pick a color, and I'm going to do everything for 2x plus y is less than or equal to 10 in that color. And then I'm going to pick another color and use that for 2x plus 3y is less than or equal to 14. That way when you look at your notes later, you're not like, well, which of these was for what? So I need that boundary line of 2x plus y equals 10. And that's in standard form. So we'd use our zeros to figure it out. And again, thumb is in front of the x here, so cover that up. And something equals 10, well, that y value would have to be 10. So it says 10 equals 10. Then cover up the y value with your thumb. Come back up here. 2 times something is 10. That something is 5. But I can't use that to drive how I label my axes because I haven't seen what's going to happen with 2x plus 3y is less than or equal to 14. So I'm going to put that color away for a second and grab a new color for 2x plus y, my boundary, 3y equals 14. And see what happens with that one to know how to do my labeling. So if we have a 0 in the x position, well then we're going to have to divide both sides by 3, and that's going to say 14/3. And then if we have a 0 in the y position, I'm covering up the y with my thumb. 2 times something is 14, and that's 7. So now I have a good idea of how I could accurately graph this, and I see, well, if I go by 1s, I'm going to be fine, because I happen to know this is a 20 by 20 grid, and we need to go as far as 10. So maybe we won't label every single one. 1, 2, 3, 4, 5. So that it doesn't get too busy on there. Same thing on my x-axis. Looks like so. And now I want to do that color coordinating that I talked about earlier. So I have my red to match my 0, 10 and my 5, 0. Then I stop and think, are we talking dashed or solid? And when I look at the system, I realize, well, all of this is solid. You know, there's equal bars for all of this. So that would be solid. And yeah, I know that's not perfectly straight. And then, by thinking about what's going on here, I can quickly put in that test of 0, 0 and have 0 plus 0 is less than or equal to 10. And definitely 0 is less than or equal to 10. So now that top equation that I completed in red, done. Have it all there. Solid, shaded, all is good. And for my blue, I have 0 and 14/3. Well, 3 goes into 14 4 times with a remainder of 2. So 4 2/3. And then 7 0. And I like that spread. I'm not too concerned about graphing that right. Those 2 points are a little bit away from each other. And you test 0 0 really quickly again. And 0 plus 0 is less than or equal to 14, so you need to shade towards 0 0. But notice I'm not getting carried away with my shading and, trying to go all 4 quadrants here. And that's because of the last 2. So the last 2 inequalities are just making sure that we stay in the first quadrant. And as we get more and more inequalities with this, you're not going to want to overshade that. So what you'll want to do is just make sure that on your graph somewhere you've represented the fact that we're going to stay in first quadrant. And that's good enough for me, as long as you've got that. And obviously from the way we set up our graph, we were staying in first quadrant anyway. So now let's overemphasize where those solutions are. And we see we have a little quadrilateral here. Are the boundaries also going to be solutions for the system? Yeah, we had solids all over the place, didn't we? So that's a yes on this one. And that does happen quite a lot in the real world, where we have solids as we're looking at this. All right. Put it all together and you get a process that's called linear programming. And linear programming is the process of businesses trying to figure out how do we maximize profit or minimize costs. And it starts with all of the graphing that we just did. A couple of years ago I was talking to somebody who had a niece that had gone to college to work on these in business situations. And she said she's often working with 20 by 20 systems of inequalities to try to figure out where the business should be working at. We're not going to go that big. So sometimes decision making in management science requires that we find a minimum or a maximum. Where should we be producing? Minimum or maximum of a linear function called an objective function. Now, a lot of times that means we want to maximize profit. That's why businesses are in this, maximizing profit. But if the economy is poor, sometimes they'll focus on minimizing costs instead. And that's when job cuts take place. So, objective function over a set of points. Such a problem, the whole thing is called a linear programming problem. We're given information that places limits on our resources. This information provides what are called constraints. Constraining something means holding it back. Usually, you don't have an unlimited supply of money. That doesn't happen. So that's a constraint. That's holding you back. And the solution of the system provides us with what's called a feasible region. The feasible region is the solution. Where is all the overlap? That's the feasible region. So producing anywhere in the feasible region is a good idea. But in particular, they want to know, where's that minimum or maximum happening? So if our linear programming problem does have a solution, it will occur at one of the vertices. So that's why it's important to graph these. And in business, they often have computers that will actually go through this process. But obviously, you have to program the computer. So you have to be able to come up with the constraints and the objective function that will make that happen. So this says we're going to solve a linear programming problem. And yes, I think we can get this in. This was the one that I said when we started out. I was hoping we could get through the one that's not a word problem. And this is the one right here. So, solving a linear programming problem, find the maximum and minimum values of the objective function f equals 5x plus 8y, subject to the constraints given by the system of inequalities. Now, if you're thinking, oh, we got to graph all that, take a look at these. And the one we just did. Notice anything? They're exactly the same. Yeah. So what we're doing here now is saying, if we had to continue this, what would we do? Well, to continue this, we have to figure out what are the vertices of this little feasible region that we have down here. I think it's pretty obvious. One of the vertices is 0, 0, and if you're thinking, I can't remember vertices, Cedarholm, where the sides hit. That's what we're looking for. So we have 0, 0, 5, 0. I think those two are really obvious there. And then, and this is why it's important to color code, you see this one right here that was on the blue. And because it was on the blue, you can come right over here and realize, oh, good thing I wrote that down. 0, 14 thirds. That was not perfectly 0, 5. But you very quickly realize that there's one here that I didn't use a ruler for when I was graphing it. I could guess it maybe looks like 4, 2, but in business, you're not going to guess. You're going to figure out where is that intersection. And like I said, most of it is going to be software driven. But that's why this space is kind of good for us here. Because what we want to do is figure out where those two boundary lines hit each other. And right now, these are the two we're interested in. So I think about those two, and I'm looking at the top one, and wow, if we did substitution, that would work out pretty cool. So if I subtract 2x from both sides, I have y equals negative 2x plus 10, and I can just substitute that into where the red and the blue lines met. The 2x plus 3y equals 14. So 2x plus 3 times negative 2x plus 10 has to equal 14. And of course, you might have looked up there and said, you know what, I'd multiply the top one by negative 2 and get the x's to cancel. There's a lot of different things you can do with that one. So substitution just jumps at me since there's a y that can become by itself very quickly. Distribute. Combine like terms. Subtract 30. And divide by negative 4. Hey, maybe I wasn't so off with my 4, 2. You know, maybe that's exactly where it'll end up. But now I know for sure that x is 4. And I have this wonderful little equation up here that I can put that in to figure out the y value. Negative 2 times 4 will be negative 8, and negative 8 plus 10 is, in fact, 2. So there are the vertices. We just got done saying that minimums, maximums will always occur at the vertices of the feasible region. So now what we have to do is figure out, well, what do you get if you put these numbers in? And I like to move these over far enough so we can have it all together here. And just a little arrow to show, hey, I know what's going on here. I know those are the vertices. And now I go back and I look for the objective function. So it's like the first thing we read as far as math goes. There's an equation there. And then we go to the constraints. These are our constraints, things that are holding us back. But this is what we need. So we're going to go ahead and put our x's and y's into that and see, since it said find maximum and minimum values, which one gives us the highest value back and which one gives us the lowest. So a 0 and a 0 will give us a 0. 5 times 5 is 25 plus 0 is 25. And we have 1 here that we might have to do a little bit of work for. So 14 thirds times 8, and it is a word problem, so if you want to do decimals with your calculator, you could do that. 37.3 repeating. And then with the 4, 2, 5 times 4 is 20, 8 times 2 is 16. That's going to give us 36. And now we just need to sum this up. And it was maximum and minimum values. So the maximum of, and the biggest one that we had was 37 1/3, occurs at 0, 14 thirds. Now, that could be bad news for people that work for this plant. Whatever it is that they're making, they're saying, well, we need to stop making X. X is costing us money. You know, we might have to lay some people off if we're not going to make X, but we're going to make 14 thirds of Y. What you got? Question? Oh, okay. Alrighty, and then we need the minimum. Of 0. Occurs at 0, 0. Again, bad news. But you know what? That's usually how the minimum goes if you're talking about costs. If we don't make anything, you know, we can pretty much shut the plant down and we won't be having any costs whatsoever. Now, there is another way to figure out where those vertices are. But algebraically, this is the way to go. But I'm going to read to you about this. Here is one way to analyze the linear programming problem in example 6. By assigning positive values to f in f equals 5x plus 8y, we obtain a family of parallel lines that sweeps across the region of feasible solutions. Geometrically, we can see that there is a minimum and maximum value for f if the line f equals 5x plus 8y is to intersect the region of feasible regions, the feasible solutions. So here's what they're saying. If you wanted to take the time to figure out the slope of the objective function and used it as a parallel line and just kept shoving it up until only one point was above it, that one point would be your maximum. And if you take that same line and you move it down, eventually 0, 0 will be the only point that's below that. So you could use that parallel process. But even the computers use intersections, everybody. I mean, they really do. It's the easiest way to figure that out. And plugging it into the objective function is not hard. So the parallel line concept, yeah, you know, it works. But most of the time, we'd rather put those vertices into the objective function to see which one gives us the biggest and which one gives us the smallest. Ben? They're going to give you the objective function, but most of the time for businesses, it's how much they're charging for the product, because that's where they get their profit. So they're charging $5 for product X, $8 for product Y, and that's where they get their money from. In terms of costs, it might be what a watt of power costs them in electricity, you know, those types of things. So depends on what it is, what particular cost they're looking at. All right, everybody. Felt like review today? Okay, good. Good. That's what we're going to call it. Tomorrow we're going to try and get through 2 word problems about linear programming, because they take a while. Now, while I'm thinking about it, I pulled out the graph paper that doesn't have any X and Y coordinates on it. You don't have to use it, but I will give you a piece of graph paper here. Yeah, you're welcome. Oops, giving you two. There you go. You've already got some.